Okay guys, welcome to Lecture 8 of Quantum Complexity Theory. This is for the Winter 2020 offering at Paderborn University. So today's topic consists of three things, as you can tell from the title: quantum interactive proofs, or QIP for short, semidefinite programs, and multiplicative weights. And you might wonder, what in the world is this little part 1 in red doing here and with a question mark? Well, the reason is because, this is, as you can tell, there are three things in this title. This is going to be a long lecture, okay? There are 13 full pages in the course notes. And moreover, each of these topics are very interesting in their own right. They're in their own rights, right? I mean, they're kind of like little nuggets that you do want to spend a bit of time on, right? It's not something that I really want to rush through. So odds are, I don't know yet, again, these lectures are essentially live, right? In the sense of how they're recorded, right? So, presumably I'll need this part 1, part 2 breakup, but question mark is, who knows? Maybe we'll go through the lecture and we'll realize, okay, in roughly 3 hours we can do it anyway, okay? But odds are this really will be a part 1, and a part 2 will be posted next week instead, okay? Announcements. A4 is due tomorrow, as you know, and A5 will be posted shortly thereafter. This will, of course, be due after the holiday break. I try not to be a jerk, at least on most days of the week, and so I'm not going to force you to work over the break, okay? Good. Of course, it shouldn't stop you from working over the break if you want to work over the break, right? I mean, it's not work if you enjoy it, right? Okay, so today's topic is an important one, and I like to, again, give a quote here that's not by a mathematician or by, somebody who works in a, say, technical field, but it's by Victor Hugo, right? And he wrote, there is one thing stronger than all the armies in the world, and that is an idea whose time has come. And, the point is that, in this lecture, we've got some really nice ideas like semi-definite programs and multiplicative weights, and these have proven perhaps unexpectedly fruitful in quantum information theory. And so in this sense, these are the ideas kind of whose time has come. Right, is what I wanted to get at with this quote. Okay, so what have we done so far in this course? In this course, we've talked about various models of verification systems, right, with various types of interaction, right? So, we started with BQP, right? And you might not have thought of this as a verification setup, but it is a verification setup, right? It's just that you just get an input X, right, and there's no proof, right? And then it just outputs 0, 1. So in this way, there's no communication at all between a prover and a verifier. And then we talked about QCMA, right, which was the same thing. Here's your input X. And now you got a classical proof. Seriously. The things I should know by now, right? Okay, classical proof. And finally, we talked about a genuinely quantum proof. Okay? So in these latter two cases, you have one-way communication, right? It goes from a prover to a verifier, and we just restrict the type of object that's sent. Good. So the most natural extension of these ideas, of course, is, well, what happens if instead of imagining that the prover sends me one message, what happens if, upon receiving the first message, the verifier then comes up with a new challenge question, sends it back to the verifier, to the prover comes up with their next message, and so forth. You have a communication protocol that goes back and forth. And that is essentially a quantum interactive proof, right? So we're going to imagine that there's a verifier, right? There's a prover, and you'll have a message. Well, you can always imagine that the prover sends the first message, if you like, and then they just go back and forth, right, with messages. And so at the very end, the prover, of course, when the prover is done sending their messages, the verifier then measures their output qubit to see if they accept or reject. Of course, we'll formalize this all later. And a key point is that right, our verifiers in all these protocols, right, they were polynomial time quantum circuits, right? In particular, they were uniformly generated circuit families. And over here with these proofs, we never cared about the cost or the complexity of producing, say, Y or Psi here, right? That was just, the question was just an existential question. Does there exist a proof? I don't care the cost of preparing it, right? This is really about a proof system in an abstract sense, right? And here, same idea, right? The prover, we're not going to restrict their runtime. They're going to be unbounded. Okay, and unbounded, of course, doesn't mean you can do whatever you feel like, because then it's not interesting, right? This just means that you just have to follow the laws of quantum mechanics. Okay, so you could apply, say, whatever unitaries you want. The unitaries don't have to have an efficient implementation in terms of 2-qubit gates. That we don't require. Okay. Good. So the two main ideas. Okay, so sorry. This is a quantum interactive proof, very roughly speaking, right? The class, we'll call it for now as QIP, and the main result of this probably two-part lecture is going to be that QIP is exactly equal to the class of languages that are decidable in polynomial space. Okay, meaning the Turing machine has a polynomial size workspace, but it can take exponential time in theory. Okay. So this part of the proof, the lecture, of course, is the part we likely won't get to today. But the two techniques we'll see along the way are, SDPs, semidefinite programs, and this is basically a very broad class of optimization problems which are surprisingly, generally speaking, solvable in polynomial time. You have to be a little bit careful, right? Not all SDPs are solvable in polynomial time. And the second is this so-called MW multiplicative weights method, right? So that first SDPs, now multiplicative weights up here. And this is kind of, the way I like to think about it is it's the oldest trick in the book for how, human beings process past events and learn from them to decide what to do next. Okay, it's the most obvious thing you could do in some sense. Okay, so again, we will cover this in detail shortly. Okay, and so the amazing thing is that all these tools that a priori look unrelated, like multiplicative weights, semi-definite programs, they all come together to show that any such interaction of this form can be simulated by a polynomial space classical Turing machine. Okay, so we're going to start by talking about the multiplicative weights algorithm, okay, which is a classical algorithm in principle, has nothing to do with quantum. So this is one of those things where even if you never do quantum again, it's a really remarkable tool to be aware of. And to boot, it's super simple, right? Well, at the very least, the statement of it is super simple, and proofs of correctness aren't complicated either, but not necessarily obvious a priori. They're not trivial. Multiplicative weights method. Okay? And for short, I'm just going to call it MW from now on. Okay, so what's the basic premise behind multiplicative weights? All right, so this is something that humans and probably animals have been even using for millennia now, which is that if something worked once before, it's likely to work again. That's the basic premise. Okay, if something worked before, likely to work again, or more likely to work again. Okay. So usually when you read up on how this algorithm is, say, introduced, it's in terms of things like the stock market, let's say, and then you have some set of advisors who's trying to predict what stocks are going to be, most productive, I guess lucrative, make you the most money, right? So I'm going to use maybe a different setting, which is maybe more appropriate for a classroom, let's say, dealing with a much more troublesome bunch, which is professors. Okay, so let's imagine that you are a first-year computer science student, and you enter your degree program, and there are all these advanced courses, and you don't know which one to take a priori, right? So what do? How do you pick kind of your path forward through your course of studies? Well, you kind of get together your A team of professors, let's say, and let's say you'll get some professors together. Let me give this, right? And you'll label them. You'll give them each like a little number, like 1 through n, okay? And what you do is, at the beginning of each semester, you ask, okay, professors, heed my call. What is the fairest course of them all, right? And each of the professors will say, will give their advice on which course you should take, which advanced course you should take that semester, let's say, okay? at the start of each semester. Ask profs which course to take. Okay? Okay. Now, in the beginning, of course, each of them will give you some suggestion, and you have no idea which of these professors knows what they're talking about and which ones, maybe not so much, right? And so, what do? Well, the only rational thing you can do is just randomly pick one of the professors and follow their advice, right? Because you don't know any better, right? So in round one, or like, let's say semester one, pick a professor I, uniformly at random, UAR, right? Uniformly at random, follow their advice for which course you should take. Okay? It's the most naive thing you can do. Of course, once the semester is over, now you're going to sit back and reflect, right? As humans, we like to learn from our experiences, right? So after the semester's over, you ask yourself, was Professor I correct, right? Did they make a good recommendation or a bad recommendation? Okay, and of course, if they're made a good recommendation, you like the course, then you're more likely next semester, when it comes time to repeat this entire process again to pick your next course, you're more likely to pick that Professor I again, right? It's exactly what you've been doing since you were a kid, right? This is how we learn, essentially. At least how I learn, and I presume how most people learn, right? Okay, and so the only question here is, so if yes, in semester 2, you're more likely to pick I. Okay, and of course, this doesn't mean that I will also be correct, always be correct. So it's not like you want to throw all the other professors in like the dustbin or something like this, right? But you're more likely when you do this randomized selection process to pick Professor I in the next round. Okay, and now the only question is, right? Think about it for a second. What's kind of the only real question here? How to update your probability distribution over profs. Okay, so you started in the first round with uniform, but how do you update it to favor Professor I, let's say, right? And the answer is, as you might guess from the name, multiplicatively. Okay? Ta-da. Okay, so that's the basic premise of when you want to use this technique, right? Whenever there's some sort of unpredictable process, and you kind of have to make decisions on the fly, right? This is going to be, by the way, you'll notice how this is in the online setting. So the algorithm we'll give is going to be an online algorithm, right? It doesn't know all the kind of the events ahead of time. It doesn't know how the courses will turn out at in each semester ahead of time, right? It has to go semester by semester, and then based on each semester, it has to make some updates, right? That's what we call an online algorithm. It doesn't have the entire input ahead of time. And it's going to turn out that this really simple algorithm is going to be remarkably effective. So this is one of those times when you really get away with something super elegant, super simple. It's kind of like black magic. Okay. So let me formalize this, right? So what do we have? We have a set of excerpts, E, and let me be clear, there's going to be n experts. Okay, so n professors, for example. And then we're going to have t rounds of some process. Okay, so the set E was your professors. Each round might be t semesters, for example. In this example we had. Okay, and what do we do in round I, right? Sorry, I want to use t for this. So we'll do t rounds, right? We have a distribution, a probability distribution, and I'll call this pt. Okay, so t again just tells me which round I'm in, right? So in each round I have some distribution over the profs, right? I'm going to sample from, so that's pt. So this is over E, over the set of profs, such that in round T, right? So let me be clear. Maybe I should be clear that this is the kind of the variable now. in round T, we pick and follow professor or expert EI's advice with probability P, T, I. Okay, so T again is the round we're in, and I tells me which professor, right? So I mean, just to be clear, this just means that in round T, I have this probability vector, right? Maybe just to help visualize this, right? And then you have some probability, maybe a quarter of picking the first prof, a quarter of picking the second prof, and so forth. And this is prof 1, and so forth, right? Prof 2. That's the basic idea. Okay, so in each step you have this big vector of your distribution. Now, a key thing, crucial, and kind of the amazing thing here is that we assume nothing. Before I state this, I need to define one last thing actually. So let me just move this down. Okay. And let's say after, or maybe I should say in round T, so kind of like at the end of the round, right? The environment administers some cost, right? So just like, you took a course and then there was some kind of evaluation of the course that took place, that's going to be our cost. So the environment basically assigns a cost to the choice you made, which was to follow expert EI's advice. To EI's choice in round T. Okay, and what we'll do is this cost will be CI, so it's the cost basically in round I for expert I. Okay, and we're going to assume that this is between -1 and 1. Okay, in our analysis. So if you get a positive cost, that will be bad, right? We're going to think of it in terms of like gain and loss, right? So a positive cost will be bad and a negative cost is good, okay, in our setting. And we'll assume nothing about how the environment sets costs. Okay? Now, as we mentioned, MW is going to be online, meaning at each stage, in each round, it's going to try and make the best choice of what is going to happen and what to choose in the next round. Okay? And what is the ideal goal, right? So what would be really, really nice? So here's the ideal, right? Imagine you could magically see the future and you knew exactly what the environment was going to give in terms of choices ahead of time, right? Then what you would probably do is you just kind of pick your favorite professor, right? The one that you know now. If you know all the choices, the costs in advance, right? Then you could tell who the best professor was going to be ahead of time, and you just kind of, again, throw the others in the dustbin and just stick with this one professor throughout the semester, right? Because they seem to know best what they're doing, right? And so ideally what you'd like to do is pick the best expert from the beginning. So let me be a little bit more formal in what I mean by that. I mean the one expert, the cost, the minimum, overall I in N, right? Sum over, so I'm minimizing overall profs here, right? So this minimization is over all the professors, and now you just sum up over the rounds, right? So you sum up the cost of Professor I in round T, right? You know, how much frustration did they cause you in that term? And you just sum up over all terms, right? And so you want to minimize that. And of course, you know, this is just one way, I suppose, to define the notion of kind of the ideal goal, right? I mean, another thing you could have done was, you know, really try and pick ahead of time what would have been the absolute minimum cost choice. That's probably asking too much, right? I mean, that's a very strong thing to do. So this is a reasonable goal, right? I mean, pick one expert, stick with it. Can you kind of simulate this cost, right? Can you come up with a strategy that, even though it's online, even though it doesn't know all the costs ahead of time, will at least, you know, approximate the best expert, right? And this is the amazing thing. The answer is yes, we can do this, even though we assume nothing about how the costs are set. Okay, now of course we won't do it exactly, we're going to do it approximately, and let me formalize those statements. Okay, so to formalize the performance of this algorithm, the multiplicative weights algorithm, I need to define just a bit of notation. In particular, I want to denote the full set of costs in each round and the full set of probabilities in each round in a succinct fashion. So what I'll do is I'll say the costs, now the full costs in any round t, now that's going to be this vector, ct. And so what is this? It's going to be a set of numbers, right, from, it's a weird looking containment. It's a set of numbers from -1 to 1. And there's not just one of them, there are going to be n of them, right? Because there are n professors. Each of them has some associated cost in round t. Okay, and then same thing for the probability vector. We already said that in round t we have a probability vector. This, of course, goes from 0, 1 because it's a probability, right, for each entry. Okay, and of course, the sum of these guys sum up to 1, right? But there's no condition on the sum of the costs of, the sum of the entries of CT. Those are just costs. Okay. Okay, so in other words, let me just be clear. The odds of picking EI, the ith expert in round I, is PTI, and the cost of this is going to be CTI. Okay, that's the notation. Okay, so the expected cost. What is the expected cost, right? Because in each round, I'm doing a sampling experiment, right? I pick a random EI, an expert, and then there's some associated cost, right? So let's just write down the expectation value in round T, right, is, I'm going to define it just as C subscript T. And what is that? Well, it's just the sum over all experts, the probability of picking that expert, right, times the cost of that expert. And what is this expression? I'm going to write this in an even simpler form, right? You can, well, it's just summing over I, and it's kind of multiplying, P1 times C1, P2 times C2, P2 times C3, and just adding these up, right? This is just an inner product of two vectors, right? It's just the inner product of PT, right, and CT. So the full, in round T, it's the full probabilities, the full costs, take the inner product. Okay, so, and this is just the notation for inner product. I don't remember if we introduced this earlier, but this is quite standard, especially outside of quantum information. Okay, so that's the expected cost in any one particular round, right? When you do one sampling experiment. And now I want to know what is the expected cost over all the rounds, and what basic but amazing tool of expectation are we going to use here to get a simple expression? Well, the expected cost, the expected value is linear, right, remarkably. Okay, so in particular, what is this? It's just going to be this sum, right, over, although maybe you don't need that. Well, okay, maybe the costs are not independently chosen, right? But the point is that over all rounds, it is going to be, I'm going to define it as C, right? So this is the full expected cost over all rounds. And that is going to be the sum over t equals to 1 up to t, right? And now the expectation of the cost in that round, that's this thing up here. And now, of course, I could just plug in my expression for each of these. That's just the inner product of PT and CT. That's it, okay? So this is the main thing I'm going to be focusing on in terms of, the cost of the algorithm we come up with. It's the expected cost over all rounds, okay? And ideally, we're going to try and kind of match this thing here, where we sum over all the costs for one particular expert, and we minimize over all the choice of experts, right? These are the two quantities we're trying to compare. This is what we're going for, and this will be the actual cost of the algorithm. Okay, so before I state the algorithm, let me tell you what the algorithm buys us, okay? And then we'll state the algorithm. So this is theorem 1. So fix any non-zero epsilon between 0 and a half. Then for any expert EI, does not matter which one, so this is important, right? I'll come back to this in a second. After t rounds, the MW algorithm, which again I have not stated yet, obtains, or again, this expected cost. This is C, right? This is the same C over here, right? So this expression up there is going to be what? It's going to be upper bounded, right? We want an upper bound on the cost, obviously. It's going to be the sum over t equals to 1 up to t of Ci of t. And let me be a little bit clear here, right? Because here, you know, first you fix your favorite I, fix your favorite expert. It does not matter which one. We have a for all here, right? Then the cost of this algorithm will be at most, so it's the same I, right? This I is fixed. The only thing that we're summing over is t in this sum. Okay, I is fixed. Sum over CIT, right? So basically the cost of that expert, if you had stuck with that expert throughout, so stick with EI throughout the whole process of capital T rounds, okay? And then, so that's the ideal cost, right? And then of course there's an error term, right? We're not gonna be perfect. So what's the error term? I'm gonna put this in brackets. Epsilon, that's the same epsilon here, times a sum over t equals to 1 up to capital T of, here again you see the I, right? Plus something that does not depend on the expert now, the ln of n, so natural log basically over epsilon. Okay? So this is the basic statement. Okay, let's just quickly parse this thing. So this is saying that it doesn't matter which expert you pick, right? And including the optimal one, right? The one that minimized this expression, right? Up here, we wanted to minimize overall the experts, right? So even if you pick the optimal one, doesn't matter which one, the cost of the expected cost of this multiplicative weights algorithm, which we're about to write down, is at most, you know, the cost of having stuck with that one expert ahead of time through all the rounds, plus something that scales with, number one, it scales with, well, what were the costs of that expert to begin with in some sense, right? If that expert was very costly to begin with, then you might expect that, you know, your error will kind of scale with that. And this one here is independent of which expert you choose, right? It's basically, you know, you can pick whichever epsilon you want here, right? The smaller you make epsilon, the smaller this gets, but of course then this blows up in turn, okay? So that's this kind of balancing between epsilon, and again, this is independent of which expert. Okay, so really think of this as kind of the additive error. Okay, cool. So let us state the algorithm now. Are you ready to be amazed at how simple this is? Algorithm 1. So, so this is the MW algorithm. So the epsilon in the statement right up here, that's going to play a role here, of course. 0, so you fix your epsilon, whatever you want it to be, right? And again, the name of the game is just like we had with our, you know, little game about having professors pick course, make course predictions, right? A priori, we're going to assume all the experts are equally good. We're going to give them an equal weight, if you will. Okay, so assign each expert EI, the weight WIT equals 1. Okay, so this is basically the weight of expert WI. Okay, sorry, this should probably say, this should probably be a 1 here. That's a typo in the notes. So here I should probably put a 1, right? Because this is in round 1, kind of at the beginning, right? When you haven't really done anything yet. You don't know which expert is the best, right? Okay. Okay, so in round 1, all the experts have the same weight. And so now you're just going to play this game, right? for t equals 1 up to capital T, right? What do? We keep going through this loop now. In each round, we do our sampling experiment, we pick expert EI, right? And now, with what probability, right? I can't pick them with probability WI, obviously, well, because, I mean, it's not a distribution over n. If all the weights are 1, right, over n terms, this is not a distribution. I have to renormalize, right? So therefore, I need to do WI over the sum of the weights, right? And now this makes sure that what I have is a distribution. Okay, sorry, I need a T in here because it depends on the round as well. Okay, so that's just a random sampling experiment. Okay, so now in that round, in round T, you pick your expert, and then the environment reveals the costs for that round, right? So then you obtain your costs. See T, right, for round T. And this is from the environment. And remember, of course, CT is a vector, right? It's the cost for all the different experts in a row. And finally, the main thing is, how do you update now your picks for next round, your distributions for the next round? And this is the trick, right? We update the weight. And by the way, we're just going to update the weights directly rather than the probabilities because it'll just be cleaner. So of course, we'll just implicitly always renormalize when it comes time to doing the sampling. So update the weight of EI as WI. And now, of course, we're going to T plus 1. This is for the next round. Maybe this should go up to T minus 1, I suppose, right? Okay. Okay. And now it depends on two cases, right? So if your prof was bad, right, meaning they caused you some cost, some sorrow, heartache, trouble that semester, then you want to do one thing. You want to reduce your weight on that professor. And if, on the other hand, their cost was negative, that means that's good. They saved you time, let's say. Then you want to increase your weight on that professor. So how do we do it? Well, here it is. WI, this is the old weight. Okay? And now it's going to be multiplicative. I'm going to multiply by a factor that shrinks the first one and decreases the second one. So let me first shrink the top one. This is in the case where the cost was positive. So I'm going to, multiply by a factor smaller than 1, so it's going to shrink. But I'll also exponentiate according to this cost. Okay? Whatever the cost was, that's also going to dictate, right, this quantity here. Okay? And now notice, the costs are always positive, right? And remember, they're between 0 and 1, right? So you should think of this, this scalar here as a fraction. Right, so let's say this 1 minus epsilon, let's say was 3/4, and then let's just say the cost was a half, right? So it's going to take 3/4 and it's going to blow it up, 3/4. It's going to blow it up a bit higher, closer to 1 up here, but still not 1, still strictly smaller than 1. And what should the other one look like? Well, now you want to increase the weight in this case because the cost was negative, and so the obvious thing to do is put a 1 plus epsilon here, so it's bigger than 1. And here it turns out that we want to use a minus this weight. Okay. And why minus? Well, the cost is negative, right? So when I put the minus, now this exponent becomes positive, right? And so then you have something bigger than 1 that's, again, it's going to be a fraction, right? So it's going to be 1 plus epsilon is bigger than 1. And when I take, say, a square root of that, it's going to shrink it a bit. But again, it's still going to be larger than 1. So you're still increasing overall. That's it. That's the full algorithm. That's the trick. The only non-trivial part in some sense is realizing, what sort of weights should I multiply by. Okay, so I encourage you to take a moment to pause this video and just stare at this algorithm until you're comfortable with all the notation, everything in here. This is one of the nice things about a video versus in class. You could take as long as you want to internalize this. And having done that, now remember our goal is to prove this, right? For any expert, I want to argue that the expected cost of the algorithm will be at most, the sum over the cost had I followed expert EI throughout, plus some additive error term. Okay? So let's do the proof. Okay. Okay, so if you remember back to your undergraduate teachings of, let's say first or second year algorithms or something like this, odds are you covered something like amortized analysis. Okay, where the idea is that you take the cost of some operation, and maybe it's very expensive, but if you do it very rarely, then it makes more sense to kind of amortize the cost over a long time rather than kind of thinking of it as a payment that can occur in every kind of time steps, right? And so to analyze to do amortized analysis, often what you use is something called the potential function. Okay, and here we're also going to use that technique. It turns out to be the right way to do this. Fancy name. So I use a potential function as basically like a reference point. And I'll clarify what I mean by this in a second. But our potential function is going to be this. So at time step t, I'm going to define it as the sum over all the weights we assigned over all experts. Okay, so you fix t, and that's how the potential function is defined. And what do I mean by a reference point? Well, the idea is that you can think of this as kind of like the center of the universe or the center of the world, and we can view other, the quantities we care about with respect to this phi t. And in particular, it turns out we can upper bound. We'll be able to upper bound phi t in our proof first, and we'll also be able to lower bound phi t. And then we just completely forget about phi t itself, right? And then we just rearrange this inequality to relate the left side to the right side, and that will give us the statement of claim. Okay, so you can think of it as kind of like crutches that help you with the proof, and at the end of the proof, you kind of throw phi t away. Okay, so let's do it. Upper bound. Okay, so let's begin. And of course, I won't go through all the steps in full detail. They're not particularly difficult, but there are exercises in the notes that will clarify some of the steps, and I'll try and point those out. Okay, so by definition, what is phi of t plus 1? Right, so again, what I want to do is I want to have an upper bound and a lower bound, right? So, instead of upper bounding phi of t up here, I'll just bound phi of t plus 1, same thing, right? So this is just the definition first. It's just the sum over all I, again, equal 1 to n if you like, of the weights. Okay, that was just the definition of this term. And now, what I'm going to claim is this. Right, so I'm going to put this in red because it's not obvious. Sum over I equal 1 up to n, right? Of what? Well, wi of t, okay, times 1 minus epsilon ci of t. Okay. And so note how, in particular, right, we've gone from t plus 1 to t, first of all. And of course, then I picked up a multiplicative term. So why, first of all, where did these terms kind of come from? Why did I lose a t plus 1 and go to t and pick up this term? Well, intuitively speaking, right, it's obviously going to have to do with the fact that in the algorithm, well, I mean, it's staring at right here, right? What did I do to go from round t to t plus 1? Well, I just multiplied by a term that looks like, 1 plus or minus epsilon, right? So when I strip off the t plus 1, that's exactly the kind of thing you would expect to show up. The only funny thing is that here, of course, I had minus plus, and here it's always minus, right? And the other thing, of course, is that c has moved from the exponent into the base here. So why is this true? Well, I'm not going to prove it here. This is going to be exercise 3 in the notes, right? So I encourage you to convince yourself that this is true, okay? And this is going to be a general statement, by the way. This just says prove that if I have 1 minus plus epsilon to the power plus minus epsilon, all to the x, right? So there's just going to be a generic statement, right? Not necessarily for our setting. Minus plus means that, this minus up here, if you pick minus up here, that means that you pick the plus in the exponent, right? If you pick the plus here, then you pick the minus in the exponent. That's what this notation means. And so you can prove that this thing is at most 1 minus epsilon x, right? For x is in minus 1 to 1. And, oh, that's also a typo. One of these things. So I think that should be x epsilon. I think it should be epsilon. This is a typo in the notes. I need to fix this. So one of these is supposed to be between minus 1 and 1. I think it should be the cost, right? Because that's what we assumed about CI, but could be wrong. Maybe I'm getting this backwards. Anyway, let's just assume that this is the case. And so, once you have this, you can just plug it in over here to get this expression. Okay. Good. Now, what do we do next? Well, the next thing we're going to do, and this is also going to be in red, because it's not trivial, right? The next thing I claim is that this is equal to phi of t, right? So the potential function in step t. And where does that come from? You could sort of immediately see this one, right? I mean, if you just expand this out, the first term here, this one is just the sum over all the wi, and by definition, that's just phi of t. So that's roughly where this one comes from. But the other part is slightly less trivial. It's not difficult, but you kind of have to expand everything out to see how it fits together. Okay. And so I claim that this is, if I multiply out phi of t times epsilon times this inner product, you'll just get back, this term here. And where's this one coming from? This is coming from exercise 4. Okay, and all you really want to do here is you want to remember that what was the probability in round I that you chose, round T that you chose the Tth expert? Well, it's just really equal to, you could write it this way, it's the weight of that expert over the normalization. And well, guess what the normalization is, right? The normalization is just phi of t. That's it, right? If you want, over here, right, I could have rewritten this denominator as phi t, right? That's all the potential function is keeping track of, is how big is the sum of the weights over time, right? Because the weights are shrinking and growing, right? Okay, so that's where this one comes from. And finally, one more upper bound. Maybe I'll do it this way. There it is. Phi of t times e to the minus epsilon ct pt. All right. So you'll notice that in particular, what's happened here is that this part has been exponentiated, right? And where does this follow from? Well, this just follows from exercise 5. And this basically asks you to show that e to the minus x is lower bounded by 1 minus x for x in this range. So how should you show this? Sanity check, right? I've got this funny looking thing, and I want to come up with a polynomial. What do? Taylor series, right? Every time, Taylor series. In your sleep, Taylor series, right? First thing you should always think of. Good. So that's the first thing we get, right? So this is just generally for any time step t, right? The potential function is upper bounded by the previous potential function, right? Times this multiplicative factor. So of course I can unroll this, right? I could set t plus 1 to be capital T now. And then I can kind of keep applying this inequality over and over again to get a bound. So therefore, phi t, kind of at the full end of this thing, what's the biggest kind of the sum of the weights could ever get? Well, it's going to be this, right? It's going to be at most n times e to the minus epsilon. And now I keep multiplying by factors of this form, right? E to the minus something, like some inner product. And of course, when I multiply these e to the minus terms together, the exponents are now going to add, right? And so that's why you're going to see a sum now. Little t equals 1 up to t of ct pt, right? That's where this comes from. So where in the world does this n come from? Right? Think about that for a second. What's left? If I'm kind of unrolling this recurrence, what has to happen at some point? Well, this is just the base case of the recurrence, right? Eventually, I'm going to get to the point where I'm going to multiply by this times phi of 1, right? And what's phi of 1? Well, phi of 1 was just the normalization at the very beginning, right? When all the weights were even and all 1. So if I sum all those weights up, well, that's just n. That's where that comes from. Good. So this is my upper bound. Okay, so this, I'm going to keep this in mind now. Okay. Now, I don't know. Okay, and then now I want the lower bound, right? The matching lower bound, as I claimed. All right, so we're going to come up with a lower bound on this potential function. Lower bound. Okay, so now we're going to do something much more basic, actually. Okay, and the basic idea is that since WIT is always greater than 0, so in any round, the weights, the way we defined it, right? I mean, if you go back to this definition of the weights started by equaling 1, right? Here it is. And in each round, I just multiplied by some factor between 0 and 1, right? Or sorry, some factor at least 0 in magnitude, right? Actually, strictly greater than 0, I suppose. Yeah. So they'll never be negative is the point. Okay, so what that means is that, this thing, right, which was the sum over all the weights in round t, that's always going to be at least as big as WIT for any I, right? Because phi is just the sum over all the WIs, and they're all non-negative. So actually, more accurately, what I wanted to do is I wanted to write in particular, I care about the case where it's phi of, okay, let me just erase these two. T plus 1, T plus 1. Okay? So at the very end of this thing, right? I suppose I want T here, right? The very last step. Because, I'm trying to get a lower bound on this thing. Okay. So, just correcting typos as we go. So, the following exercise says says this. Okay. So what are we going to do? So I'm going to start with phi of t, right? And then I want a lower bound on this, right? So it's going to be wi of t for any wi I choose, doesn't matter which one. And now the point is that, I want to lower bound this thing by something, right? So what am I going to do? Well, there are two exercises that kind of come into play here. So first, exercise 7, I'm going to go backwards here. Exercise 7 says that the ln of WIT, okay, because a ln is just going to make things a bit nicer, but of course, if I want a lower bound on WI, I'll just exponentiate it again to base e. This thing is going to be at least minus epsilon, the sum over I, ci, t, right? So the costs basically in round t, minus epsilon squared times the sum over I of ci t. Okay, this is the claim. So let's just parse this for a second, right? What do I see showing up here? Well, these are the initial costs basically of expert I, right? If I had picked that expert throughout, okay? And this is that same thing, but with absolute values, right? And where did we see these terms? Well, we saw these terms, let's go back to the statement of the theorem. The statement of the theorem is right over here, right? These are the clean costs, if you will, of expert I, and then we had the absolute value version, right? Those are the two terms you're seeing down below, okay? So let's go back. Oh, and the other thing I want to point out is that I wonder why I don't see a base E here somewhere. Oh, that's right, that's right. Good. So what you're going to do, of course, is now over here, you're going to plug this in, right? Take this thing, plug it over here, right? And that lower bound, of course, now I want, this is a ln, right? I don't want that, right? So what I'm actually going to do is I'm not going to plug in that. I'm going to do e to this thing. If I call this x, I'm going to do e to x, right? And that's going to be my lower bound. So I have e to something. And that's kind of weird because if you look at the statement of the theorem, there's no e, there's no base e in this theorem, right? I mean, look, none of these guys are exponentiated. So what in the world is going on? Well, if you go back to our upper bound also had a base e. So you're going to have base e on both sides, and of course then you'll take the ln of both sides. Okay. Alternatively, of course, you could have just taken the ln of this to begin with and just plugged in this directly. So the point here is that if you believe this claim, this one right here, okay, or sorry, this claim, then if you just plug it in, right, you should get the claim. Okay, combine with the upper bound to get the claim. Okay, because then you just get the sequence of inequalities as I'm pointing out here. Why is this true? Why is exercise 7 true? Well, technically speaking, it relies on exercise 6, which is just kind of a clean math statement. Prove that if epsilon is between 0 and 1/2, right, then the ln of 1 over 1 minus epsilon is at most epsilon plus epsilon squared, and the ln of 1 plus epsilon is at least epsilon minus epsilon squared. Okay, so again, I'll leave that to exercise, but this is how you prove the statement of the claim. Okay, so very simple. In each round, we just update our weights on each expert, and then the analysis uses this potential function, which both you put down upper and lower bounds on the potential function, and then you throw the potential function out, and then you just combine the upper and lower bounds, rearrange, and you'll get the claim you want. Okay. So this is the basic multiplicative weights method, and a really good resource for this kind of stuff is you can look at, this is in the notes, you can look at the PhD thesis of Satyen Kale, which is available online. And I'll just leave it at that if you're interested in multiplicative weights. There he fleshes out how to generalize this to the matrix setting. We're going to kind of sort of skip a step and apply this technique directly to the quantum setting, which of course is a matrix setting. Okay, so our goal, having introduced multiplicative weights now, is next to talk about quantum interactive proofs and semidefinite programs. And those are just STPs for short. Okay, and so of course our ultimate goal is to come up with a matrix analog of multiplicative weights. Okay, and that's going to be used to show that Q of P equals to P space. But before I do that, we need to define what a quantum interactive proof is. And second, we need to write down the optimal acceptance probability for an interactive proof as a semidefinite program. Okay. So let's start in 2.1, quantum interactive proofs. Okay. So, classically interactive proofs are an extension of NP, right, where you have a bounded running time verifier, right, and a prover who's unbounded, and they exchange messages back and forth, right? So QIP is going to be the quantum analog of this, as we discussed in the outset of the lecture, okay? And so the question now is, in the quantum setting, right, what does it mean to send back a message back and forth? I mean, of course, this makes sense intuitively, right? But how do you formally model this, right? And it turns out, so how to model communication, right? Between the prover and verifier. Okay. So the basic idea here is that we imagine that there's one designated register. Okay, so there's a designated register, and I'll just call that M for message. Okay, and basically they're going to take turns passing this register back and forth. At least that's the way you should think about it. Of course, when we write down the formalism, that register is not going anywhere, right? I mean, it's just some static division of the full space into various registers, one of which is going to be M. And the point is that they'll take turns kind of acting on M, right? Which will simulate this idea of sending a message back and forth. So here's the formal definition. So I'm going to first start by generalizing the notion of a QMA verifier, in which there's just one round of communication, right? The prover just sends a message to the verifier, and the verifier just goes ahead and does the verification. And let's generalize this now from a one-round quantum verifier, which was QMA, to an M-round quantum verifier. Okay, that's the first thing we need, right? So first I need to define the verifier. Then, of course, on the other side, the prover will be defined in a very similar fashion. And then we can couple these together to get the back and forth interactive proof. Okay, so an M-round quantum verifier is what type of circuit family? Well, what we do should generalize QMA, right? So I can't just put down any set of quantum circuits. It's got to be P uniform. Quantum circuit family. And so let me just use Q. And now this is going to be a set of circuits, right? Originally for QMA, we just had one circuit, right, for each input size n. And here instead, I'm going to have a bunch of circuits for each input size n. Right? I'm going to have m of them. Let me put down that m and really clarify. There it is, right? Why m? Well, sorry, this is... So the n should come first, and the m should come second. So why m? Well, because now you have m steps that this protocol is going to take, right, back and forth. So there are going to be m circuits which need to be applied for input size n on the verifier's end. Okay. So that's why you see m circuits. So it's one circuit per round, and these act on 3 registers. And the first one generally we're going to ignore to maintain some cleanliness in the writing, right, to just drop some notation. So an input register A, right, and this contains just the input. So it's an n-bit input, right? It's the same n as you see over here, right, that dictates the size of the verification circuit. Okay, then you get to a message register. This is what we just talked about. M, right, so maybe I'll do that one in red. Maybe I'll do all these in red, right? So input, message register, and this is going to be some P of n qubits. P is some polynomial. P a polynomial. Okay. And because that just means the message size is, of course, polynomial. And then, of course, you have this ancilla space, right? Let me not call it ancilla. Let me call it private register, because now there's a notion of, you know, each player here, the prover and the verifier, they have their own kind of private message space, right? And those will jointly be part of this private register, basically. V, and this is going to be Q of n qubits. Again, Q is a polynomial. Okay, so what do? We imagine this is the verifier, right? Verifier acts in rounds. Okay, so what does it do in round I? In round I, it applies the ith circuit, right? Q, n, comma, I. Okay, there's the I. By the way, you know, soon I'm going to drop this subscript n you see over here. I'm just doing it in the beginning to be consistent with QMA, but, you know, we're going to fix the input size anyway, right? Okay. Okay, in rounds, and at start, as usual, we imagine the, you know, M and V, you know, these two registers, right? The message and the ancilla, those are initialized to all zeros. Okay, just like we normally do for QMA. Okay, so, you know, stare at this for a second. Make sure you convince yourself that it really does generalize QMA, right? What's the main difference? I mean, you can pause the video and think on your own. Normally for QMA, we would just have, say, the first circuit in the sequence, right? Because there'd only be one message, essentially. But now we have little m messages. Okay, and to simulate kind of this back and forth communication, we're going to do it via some third message register. Okay. And of course, by the way, this message register used to be called the proof register for QMA, right? Because then the proof would get sent in this register. But now the point is that we're going to reuse that register. Once you receive the proof in that register, then you can kind of swap it out and put in something else and send it back, essentially. So this is for the verifier, right? And of course, the verifier has to talk to somebody, right? This is not a one-player game, it's a two-player game. And so I'm going to define the corresponding notion now of an M-round prover. M-round quantum prover. Okay, and so the definition is, I think, almost the same, if not exactly, just one thing is off. Okay, so same as definition 8, except, what's the difference? Can you think about it? So take a moment again, pause the video, and see if you could figure out what the difference is. Okay, what's the only difference? The only difference is that, remember, unlike the verifier who is bounded to run efficiently, the prover is not bounded to run efficiently. Okay, so that means that you see what I wrote in red over here. This P uniform part, we can drop that now, right? I mean, as long as you follow the laws of quantum mechanics, the prover can do whatever they want. Except not necessarily P uniform. So we basically just follow quantum mechanics. Okay, so that just basically means that they're just going to take turns applying some arbitrary unitary on the prover's end. Okay, we don't care about the efficiency of implementing that unitary. Okay, that's definition 9. Okay, so what does a quantum interactive proof look like then, if I were to kind of write out the action in an algebraic sense? So here is a, let's say, an algebraic sketch, if you will, of a quantum interactive proof. You start with what? Well, in the very beginning, right, all the registers are zeros. And maybe I should have said MV and, well, the input register not, right? And so what am I going to do? I'm going to, yeah, so maybe over here, let me make one note here. Now the private register, this V, right, the workspace, right? This is technically split between both the prover and the verifier, which they each get their own private space to work, right? And they're not supposed to look inside each other's private space, okay? And so let me just call those, give those two private spaces different names to distinguish, right? So P will denote prover's private space. Sorry, private space. And V will denote the verifiers. Okay, so henceforth, you know, right now I'm going to write down some labels that will correspond to, you know, whenever I write down P and V as a subscript now on these kets, that's what it's going to mean. So for example, here, this is going to be the prover's ancilla space. Okay, only the prover sees this. Okay, and on the other hand, you have over here the verifiers ancilla space. Okay, and what's the common shared space they have? Well, they have the shared message space. Okay, which they take turns sending back and forth. Good. And so what happens here is now we take turns, right? So first, we can imagine without loss of generality that, say, the prover acts first. So the prover maybe applies some unitary. This is an arbitrary unitary, by the way, because it's the prover who's unbounded. And what spaces does this act on? Well, it acts on M, right, this message register, right, and it acts on P, because the unitary they apply is going to be in their private workspace, but it can also be, and should also, of course, be on the message register M. And of course, technically speaking, that means that there's an identity here on V, right? Why? Well, the prover can't see the verifier's private workspace, right? That's what this is. So it should be tensor identity on that space. Okay, but you know, we're not going to write that down. I'll just keep indexing the registers. Okay, and then I'm going to say, remember we defined this verifier to have circuits QI, right? And I'm just going to drop the little n from now on. Okay, so first it applies Q1, right, in the first round. And what spaces does that work on? Well, first it applies to register V, right, this one now, right? But of course it also acts on the message register, right, because it needs to send a message back. That's one round. Okay, so that's like saying Q R, well, what am I doing that for? Let's just say verifier prover, right? There are two boxes, and now the prover first sent their first message, and then the verifier sent their first message back. Okay, that's what we see. And of course, you could repeat this over and over again. There are little m rounds, right? And so the last one will be Rm. Okay, and don't forget this is an arbitrary unitary, and this one will be P uniformly generated. Okay. And so this one is going to be what? It's going to be on the message register, again on P. And finally, we can assume that the verifier acts last. Why is that true? Why can we assume the verifier acts last? Well, it's because they're going to make a decision, right? If the prover sends another message after the verifier already measured, like who cares at this point, right? It doesn't change anything. Okay, and so now we assume that the output qubit of QM measured in the standard basis. Okay, so that's essentially what would have happened in QMA, same thing. Okay. Good. So that's the basic definition of having a prover and having a verifier, okay, formally. And now, of course, I need to piece these things together, right, to come up with a formal notion of an interactive protocol, okay? And of course, then I'm going to start talking about things like completeness, soundness, right? So these are the set of problems that can be verified by an interactive proof, basically. Okay, so definition 13. Quantum interactive proof systems. Okay. Okay, so again, promise problems, right? Don't forget, promise problems. I suppose I want to say A equals to A yes, A no, invalid set. Oops, let's not do that. Okay. What is this thing? Right here. Is in QIP if there exists a polynomial M okay, and an M-round quantum verifier. Okay, so again, the verifier is the one we kind of fix ahead of time, right? So that's kind of one half of the jigsaw puzzle, if you will. And now we want to argue about whether or not in the yes case there should be kind of a good prover that you could fit into this jigsaw, or that'll make you the verifier accept with high probability, or in the no case, no matter kind of what prover you fit in here, it's just not going to do very well. Okay, so an M-round quantum verifier, such that for all inputs X, we have completeness soundness as always, so I'm just going to say yes, no case for brevity. So if X is a yes case, there exists an M-round quantum prover causing the verifier to accept with probability, say, at least 2/3. Okay. And no case is exactly what you think then. If X is an A no, for all M-round quantum provers, the verifier accepts with probability at most 1/3. Okay? And as usual, in the invalid case, we don't really care what happens. Right? In the sense that, again, the verifier can output whatever it feels like with whatever probability it feels like. Okay. Okay, so that's the very basic definition of a QIP protocol. Again, the key components here are what? You have your M-round quantum verifier on one side, right? And then you're trying to couple it on the right with this M-round prover, basically, right? And in the yes case, there should be a good prover that will convince the verifier to accept with high probability. In the no case, doesn't matter what prover you come up with, you're going to reject with high probability. All right, that's it. Now, there is a bit of magic that we're going to use here. Which is that, normally, certainly in the classical case, when you're just having a classical interactive proof, it's generally believed that, you really do need super constant number of rounds, like say polynomial number of rounds, to capture the power of the class. But quantumly, this is not true. Quantumly, it turns out you can squish the whole thing down into just a very simple looking protocol, which is just a constant number of rounds. One round of which is even more simple, is just a single coin flip. Okay, that's completely independent of everything else. So let me make this note because we're going to use this in our analysis probably next week, but certainly later in this overall lecture. Okay, so suffices to use 2 rounds. Okay, by which I mean we're going to have what? 0 in the verifier register, 0 in the message register, 0 in the prover register, right? And then first the prover goes, right, on message and prover. So this is prover, right? Then goes the verifier. So verifier message. Then goes the prover, R2. And finally, one last round. Of course, now we get to decide what to do. Good. So we can truncate here, it turns out, without loss generality and still capture all of QIP. And this one here, not only that, this box here, right? This is the message, the intermediate message from the verifier back to the prover after they got the first message, right? So in our picture, it looks like this, right? Here's my verifier, here's my prover, and so we had first one goes this way, then one goes this way, then one goes this way, right? So just 3 messages. And so this one over here is this one, right? It's this arrow here. That one we can assume is an unbiased coin flip. Okay. So in other words, your prover first kind of commits to a message in the first round or in the first message, right? Some quantum state. And once they've committed to that, then you can flip a random coin and tell them the coin, right? And in our case, the random coin will correspond to one of 2 measurements you're going to run. And then based on that coin flip, the prover will then send the rest of their quantum state. Okay, so you should really sort of think of, they send half their quantum state, then they get a bit. Based on that bit, the prover decides, they only hold this much of the state left. They already sent half of it off, right? So on the rest of the state, it's going to apply some local unitary to kind of rotate things around and make it nice, and then send over the rest of their state. Okay? And I'm also going to assume completeness soundness parameters. So turns out we can assume perfect completeness, and versus a half plus epsilon for any epsilon strictly greater than 0 soundness. Okay, so in our analysis, towards the end of this lecture, these will be the bounds we use. Okay, and remember this is in contrast to QMA, for which we don't know how to get perfect completeness. For QCMA, we can get perfect completeness, but we did not cover that explicitly in the lecture. Good. So that finishes our definition of QIP. And now what I want to do is I want to show you how to embed QIP into a semi-definite program, basically. So let's see if we get to exactly that in this lecture. I certainly want to talk about semi-definite programming. But I want to take a little bit of time to do this properly because, it's a beautiful optimization framework. It's worth knowing about, seeing at least once in your during one of your degrees, let's say, in the university, and it's proven remarkably useful. Okay, so, and I wouldn't consider myself certainly an expert on things like optimization, like semi-definite programming, things like this, like context optimization, but So I don't exactly know how often semi-definite programming gets used in practice, though there are certainly solvers you can download that work quite well. But certainly its kind of baby brother, linear programming, gets used all the time in practice. Okay, and it's remarkably quick to solve. Okay, so I've already said the words like linear programming and semi-definite programming. And the first thing that kind of comes to your mind as computer scientists is probably, like, what, we're going to start coding now? Like, that's weird. We've never done any coding in this course. And the answer is no, we're not going to code, right? We're theorists. And not that there's anything wrong with coding, right? Programming here just means that, semi-definite and linear programs are just going to be optimization problems. They're just families of optimization problems that has absolutely nothing to do with writing computer code, okay? And so basically, like for linear programming, what kind of optimization problems are we interested in there? Roughly speaking, the basic idea here is you want to maximize a linear function. Okay, so f, so you give me some set of variables. There are a little n of them. And based on that, I just give you some value for this, for the function you're trying to maximize, right? This is usually called the objective function, as we'll see again later. So we're trying to maximize this objective function, and of course what makes this interesting is the fact that there are some constraints we have to keep in mind. So subject to a set of linear inequality constraints. Okay, so that's the basic premise of a linear program. And I don't want to say too much about this, right? But it is, where was the last time? Oh yeah, okay. It is, as I said, a very, very useful framework that gets used all the time in practice. And again, you could talk full lecture, well, you could fill a whole semester full of, lectures on linear programming if you like, right? So obviously we're not going to do that. We're going to jump straight to semi-definite programs. And a semi-definite program, the idea here is that, look at the variables here, right? I'm optimizing over this space, right, Rn. So the variables are going to be these n-dimensional vectors. In a semi-definite program, we're going to generalize this. So from now on, I'm just going to write SDP, right? The variables are going to be matrices, okay, variables. And not just matrices, they're going to be Hermitian matrices. So why are they going to be Hermitian matrices? I claim you can answer this question without knowing anything about LPs and SPs other than what I've written on this slide. Take a moment to pause and think about that. Okay, Hermitian is what? Right? Hermitian is what happens when you take an n-dimensional vector and you put it onto the diagonal of a matrix, right? Otherwise zero matrix, and then you just change basis by conjugating by a unitary, right? So that's why it's a natural thing to do, to talk about Hermitian matrices. Okay. Okay. And okay, so in particular, they're just linear operators which act on, say, Rn. Of course, you could also make this complex if you like. And well, actually, I did that in the notes, so you can do that if you like. Whoops. Okay. And instead of using, here we said linear inequality constraints. Like maybe you could have said something like, the second variable, it has to be at least 2. Like those are the types of constraints you can put down if you like, for example. You could also do things like x1 minus x2 is at least 2. So there you had n variables. And now we have to generalize this notion of inequality, right? Because that only holds for scalars, and I don't have scalars anymore, right? I've got matrices. And so here we want to use this generalized inequality, which again is a fancy word for something you actually already know. This thing, right? You've seen this before, right? And so what does this thing mean? It basically says that you want to say, you can put down constraints of the form. This is subject to. So you do this, you're going to do an optimization over Hermitian operators, variables of this form, subject to constraints of this form. And so what does that even mean? Well, if I say that, Hermitian matrix A is at least as big as Hermitian matrix B relative to this generalized inequality, the way we define that just says that the matrix A minus B is positive semi-definite. Okay? So just put everything on one side, you're allowed to do that, is PSD. Okay, and this you already know, right? I mean, we've been using this terminology for a while now. Okay. And that's where the term semidefinite comes from, okay, in semidefinite programming. Okay, so that's just like a high-level preview, obviously. That's not a formal definition of semidefinite programs in any sense. Let's just play with this for 1 second. I just want to do an example. So, let me just get you a little bit comfortable with this, right? So, for example, is it true that, let's just talk about qubits, right? This is just Pauli X. Is it true that identity is larger than Pauli X in the relative to this generalized inequality? Okay, so let's just do this together, just to get you a bit comfortable with this. So let's rewrite it in the way we said here, right? I mean, this is true if and only if identity minus x is positive semidefinite. Okay. So I mean, if you're comfortable with, there are various ways to kind of see this, right? If you're comfortable with just spectra and of linear operators, then you can kind of read this off right away, right? Because the eigenvalues of identity are all ones, right? And we know that the spectral norm of x is at most 1. In fact, it's also exactly 1. So kind of the smallest number you can get out of this difference on for an eigenvalue is going to be 0, right? I mean, because you can have, at best, you can have 1 minus 1. Okay, that's kind of waving hands. I mean, we can make this a bit more formal. If you want, you could always rewrite this as in terms of spectral decompositions, right? What was x? X is just plus plus, minus minus minus, right? In terms of its spectral decomposition. Identity is just plus plus. Minus minus, right? And then if you just add and subtract terms, right, these terms will die off, right? And then you will get 2 times this thing, right? And this thing is certainly positive semidefinite, right? It's the projector, right? Check. So that's one way to see it, right? So formally speaking, the other kind of route I was sketching is you could write that identity minus x is certainly going to be at least as big as identity minus the infinity norm of x times identity, right? This is a scalar now, so I could scale the identity. And so therefore, as long as the infinity norm of x is at most 1, then this thing is going to be bigger than or equal to 0, right? And why is this true? Well, this is just because I've implicitly used this fact here that an operator x, doesn't matter which one, is always going to be at most its norm, the largest kind of eigenvalue or single value in some sense, times identity. Okay, and I'll let you convince yourself of that fact. Okay, because I mean, what are you really doing? This has some set of eigenvalues, so you're just kind of pulling out the biggest eigenvalue. That's a bit of a lie because here we're talking singular values, right? And then you scale the identity with that, right? So you hit the identity has all its eigenvalues this big, and the eigenvalues here are going to be at most this big, potentially smaller, right? And so clearly this thing will have bigger eigenvalues than this one. Of course, here I'm really crucially using the fact that identity diagonalizes on any basis, including the eigenbasis of x. Okay. By the way, as a good sanity check, you could ask yourself, another reason why we use Hermitian operators, right, to define this. Like, why didn't I just use, say, more generally normal operators, right? Normal operators can also be diagonalized, so in principle, I can think about comparing eigenvalues, right, in this fashion, right? Because this just says that the eigenvalues of this operator are greater than or equal to 0, right? But remember, normal operators can have complex eigenvalues. If you have complex eigenvalues, then, it's not really well defined. Well, you have to be maybe a bit more careful how you define your inequality, right? How do you define one complex number as being bigger than another, right? Okay. And presumably you could put down an absolute value or something, right? But at least the plain vanilla definition makes no sense, right? I mean, you can't say that e to the I theta is bigger or smaller than, say, 1, right? That's a weird comparison to make, right? All right. So, where do I want to go? Good. another exercise that's really worth doing, exercise 16, right? If A is positive, B is positive, does this imply that AB is positive? Okay. So, and you should really compare this with, I think that means compare with, but let's not try and be fancy. Compare with A plus B, right? So originally, certainly we've seen this already, that if A is positive, B is positive, then the sum of them is also positive, right? And you can sort of see this as, well, I don't want to use this analogy because it's actually not correct when it comes to multiplication, right? Okay, so this one is, this is true, yeah, this does hold. And the question is, does this one hold? And, well, there's kind of an easy way to see this, right? Which is that for something to be positive by definition, right? So the answer is obviously no. I mean, otherwise I wouldn't spend time talking about this so much. And of course, this is in stark contrast to the case of scalars, because if I have two positive numbers, I multiply them, obviously classically I get something positive, right? It's a bit ridiculous otherwise. So what's wrong here? Well, remember that to be positive, you had to have two properties, right? You had to, number one, be Hermitian. Number two, you had to have non-negative eigenvalues, right? So let's take a look at AB, right? Is it Hermitian? I mean, the eigenvalues are a little bit hard to say anything about. Let's be clear. If I have eigenvalues of two operators, I multiply these things together, there's not too much you can say about the eigenvalues of the product. I mean, you can make some guesses as to the ranges as to which they'll fall in, but beyond that, it's hard to tell, right? Okay, so is this Hermitian? Well, what does that mean? Let's check its dagger, right? The dagger of this, it's supposed to equal to AB, right? But remember the properties of dagger say that it reverses the order of the multiplication. This is because of the transpose that's hiding in the dagger. And now, what we wanted this to equal to was, this should have equaled to this, right? If it was Hermitian, then the dagger shouldn't have changed the operator. So what you're basically, A and B are positive, by the way. So let me take an extra step here, right? That means that they're Hermitian, so certainly I could write this, right? They're positive. And now the question is, do I get the original operator back? And now you see that in order to be Hermitian, a necessary condition is in fact that A and B commute, right? Only if the commutator of A and B is 0. That's it, right? So if these operators don't commute, their product is not even going to be Hermitian. Never mind talking, like, so it's not even going to have real eigenvalues in general. So you can't even talk about it having non-negative eigenvalues. But if they commute, it's fine, because then BA can just be swapped back around to AB and you have a Hermitian operator. Okay, so usually, again, one of these life lessons in this course, right? Anytime you see some new notation, one of these really kind of beautiful concepts like a generalized inequality, put down your book or whatever you're doing and just play with it a little bit. Make sure you understand some basic cases, like we did here with like I versus X, or just checking some closure properties, right? In which in this case doesn't hold, right? A and B can be positive, but the product maybe not. Okay. Good. So with that said, now I can define a standard form for semidefinite programs. Okay, and let me be clear that a semi-definite program, generally speaking, is going to be an optimization over Hermitian operators. The objective function is going to be some linear function, and then you can put down these generalized inequality constraints. Basically, that's how this goes. But you can take any semi-definite program and write it in a very special standard form, and that's the one I'll write down, just so we have some sort of canonical form to work with. But often in practice, you won't necessarily need to do this. It depends. Like sometimes if you want to actually pick up an actual solver, an STP solver, I think, like MATLAB certainly has one, and Mathematica might have, I'm not sure. It's been a little while since I've played with these. But certainly I've used them, and they're a lot of fun to use. But the part of it that's not fun is that sometimes they might ask you to take whatever STP you have in your specific setting and rewrite it in a certain standard form. And that can be a bit of a pain, but it can be done. Okay? So what do we need? We need 3 ingredients. Number 1, we need a cost matrix. Okay, so this is just some Hermitian operator, whoops. And it's acting on some space x, whatever x is. Okay, second thing we need is a constraint matrix. Okay, so the cost matrix is going to be using the objective function, right? That's going to tell us how the costs scale relative to the parameters. The constraint matrix is going to be used, well, to constrain the variables, as you might guess. And this is on some other space y, whatever that is, right? And now we're going to have a linear constraint map. And you'll see kind of how this comes into play. And this is something funny. I mean, it's something we're not going to really formally define in this course. I mean, it's a mathematical map. It's certainly well defined. It's a map that's going to take a Hermitian operator on your variable space, if you will, where this was defined, right, where the cost matrix was defined, and map it to a matrix on this constraint space. And that's why it's presumably called a linear constraint map, or a constraint map in general. Of course, it's going to be linear because of its properties. Okay. And so these are the three ingredients I'm going to need. So let me show you, let me just write down the full semi-definite program. It just takes a few lines. And then we'll try and digest this thing. Okay. So semi-definite programs come in what are called primal dual pairs. Okay, so on the left-hand side, I'm going to write down the primal STP, which I'll just denote P for primal. This is kind of like the main STP, if you will. And corresponding to this will also be a dual STP you can write down. And for now, I'm just going to sort of ignore it, just going to keep writing these duals down without really telling you what it is. But of course, we're going to use this in a very nice way. Okay, so there's a very beautiful duality theory in linear programming and semi-definite programming as well, and more generally in convex optimization. Okay, what's the primal problem? So we're going to take a supermem. Okay, so it's not a max, it's a supermem. We're going to talk about this in a second. And what do we see here? Well, first I need my first ingredient, this one. Okay, let me use my cost matrix. There it is, C. And what's my variable? Let me write this one in maybe blue. There it is. So this is going to be my variable. Okay, so I'm maximizing this inner product, basically. This is fixed, this is not. Remember, trace is a linear function, right? I don't have funny powers of x. This is just x to the power 1, and I'm hitting it with a scalar. Okay. You should think of this as the matrix analog of just ax, basically, something like this. Okay. Where those are both scalars, of course. Okay. Subject 2, which constraints? Well, the next ingredient I had, so so far I used this one. The next ingredient I have is my constraint matrix, right? Okay, let me put down the constraint matrix next. The constraint matrix is going to be part of some constraint, obviously, right? So I'm going to have some sort of constraint. I'm going to put it in this direction right now because we're maximizing the objective function. So I want to upper bound things in the constraints so that they don't go off to infinity. And so here I'm going to put in the D. Okay, so that's my constraint matrix. That's going to upper bound things. And now the question is, what goes on the left-hand side of this? Well, most generally, right, this cost function, and hence x, right, these act on the same spaces, right? We're assuming they're square, of course, because they're Hermitian. They act on x, right, but D can act on a different space y, right? So on the left-hand side, I want to have some function of my variable x, right? But I need to kind of potentially put it through another map for us to take it from the space script x to script y. And that's precisely what this constraint map was for. It buys us this generality, okay? And usually this is actually necessary. This is not like some sort of weird generalization that nobody really cares about. So there's my constraint map. Now I've used part 3. And here I put in x, right? It's going to take x to the right space so that this inequality will make sense, okay? And the last thing is that we're going to ask that x be positive semi-definite, okay? Again, which I'm allowed to do. That's your primal STP, that's it. Okay, and of course, this is, it looks very short and abstract, but of course, this can be quite complicated, right? I mean, this can be an arbitrary linear map, essentially. Well, as we'll see shortly, it can't be exactly arbitrary, but it'll be very, very general, okay? let me show you the dual problem. Now, in this course, we're not really going to be concerned with how you find duals, right? There's two ways to do it, at least two ways, obviously. The first way is that once you put your STP into the standard primal form like this, so meaning you write down your C, your psi, and your D, then you can just immediately write down the dual. There's going to be a formula I write down, okay? If you don't want to do it this way, like maybe it's just really nasty to put your STP into primal form already, like to begin with, right, so that you could apply this immediate mapping, then one thing you could do, for example, is go back to first principles. You apply something called Lagrange Multipliers. Okay, so there's a way to do this. It's more difficult than it looks. Like once you get the hang of it, it's actually very easy and mechanical, but it's very easy to make mistakes. You have to be careful. And there's a lot of notation involved. If you're interested to learn more about the theory of convex optimization in general, I very strongly recommend this very nice book by I think it's Boyd, and I think this is how you spell his last name, Vandenberg. Let me see if it's here. Okay, no, it's at home at the moment, so I can't check that last name. But certainly if you look at the first name is certainly Boyd, and you'll find it, okay? Great textbook. May or may not be free legally online. I think on their own, I think on their web pages even, they have like a draft PDF version, so it's worth looking up. Obviously, don't do anything illegal. If they have a legal version, do look that one up. Okay. Dual STP, right? Look how simple this is going to be. You're going to have a variable y. This is going to be a scalar now. This is just a complex number. Okay. Subject to. Oh, sorry. I skipped ahead of myself. So it won't be that simple. I take it back. I was wondering why it was so simple. Trace of y is going to be my variable, my dual variable. Now it's a matrix. Sorry, it's not a scalar now in this case. And now I'm going to have some other cost function, some dual cost function, d instead of c. And you'll notice, well, let me just write the whole thing down maybe. I'll have to define the star operation. I haven't defined that yet. Phi star of, oops. Okay. Y is greater than or equal to 0. Okay. So first, just stare at this thing for a second, right? The new variable is this one now, y. Okay, it's not necessarily related to x a priori. Also a matrix, right? And then you see these other three terms. You see d, right? You see c, and you see psi star. So what in the world are these things? Well, you just have to, shift your eyes over a couple of centimeters over to, I'm not sure whether it be your left or your right. But in my case, I'll just go look a little bit to the left, and here they are, right? Right, there's d, right? There's c, right? It's just the exact same operators. They just kind of move over, right? So once you have yourself this standard form on the left, the dual is very easy to write down. Well, with a little asterisk, if you will, and that asterisk is precisely this thing over here, okay? So you do see the same constraint map. It's just that we don't have that. We have the adjoint of the constraint map, the star. Okay, now I need to define this, of course. And finding that, it's not difficult, but again, it's one of these things where you just need a bit of practice and it takes a little bit of creativity as well. Okay. Maybe I'll define the adjoint first. Or maybe should I leave that? No, okay, let me leave that to the end. Okay, so let me just make some notes. The last of which will define that psi star business. So again, the variable, well, I should say the primal variable is x, right? As we said, that's what we're optimizing over on the left-hand side, okay? So let me just maybe do this. And so the feasible region is the other thing I want to define, feasible region. Is what? It's going to be the set of all valid assignments. Okay, so what do I mean by valid assignments? That means that just the set of all settings to x, my variable, such that So all x satisfying the constraint, right? Psi of x is at most d, right? This one over here, right? That's this one. Okay, so satisfying that constraint. Of course, sorry, there's one more. Also, we need that x is positive, right? That's this last constraint. So satisfying both of those. That's my feasible region. Okay. And maybe here I could put a bullet point. Let's do another one here. So the objective function is trace of cx. Okay, and you can think of it if you like. I mean, you can think of this as, some f of x, right? Which takes in the matrix x and is just some function, right, that maps it to a scalar. You can think of it that way if you like. F is linear, so what does this do? This takes you from a Hermitian operator on x, right, and it maps you down to a scalar, right? That's precisely what this thing does. Technically speaking, we know it will be real. Why is that? Well, the eigenvalues of a Hermitian operator are always real, right? And so all I'm really, well, sorry, I take that back. I suppose C could be, is it real? Do we make it real? Okay, well, let's just assume that it's a linear a real function so that it makes sense to maximize things. Presumably, you can do that in general. So let's assume it goes to the reals. Okay, and notice that a lot of times what you'll see is that we can write this as the inner product between matrices C and X. And the usual definition is this is the so-called Hilbert-Schmidt inner product, right? And this just says the trace of C dagger X. That's the formal definition. But C is Hermitian, so the dagger doesn't matter. Okay? So a lot of times we'll just write it this way, this objective function. Okay, and a nice little exercise is that prove that exercise 17, prove that this objective function is linear in X. Okay? And that's a trivial exercise. The harder part of that, it's not really hard at all, but it just makes sure that you understand the definition of linear, right, in terms of variables. Okay, so I strongly recommend you do exercise 17. You might wonder why in the world, I think we've talked about this, right? But the reason why, we think of this thing here as an inner product is simply because if you take C and X, right, and you stretch them out in the right way into long vectors, each of them, and then take the inner product between these funny stretched out vectors, it'll turn out to equal to exactly this thing here. Okay, and that's essentially why we think of this as an inner product. I think we mentioned this in one of the early lectures. But regardless, that's exercise 18, which again, I encourage you to try your hand at. Good. Now this map here, this psi that takes x and maps it from the space script x to script y so that I can compare it with d, which lives in the y space. Psi must be, so it's got to be linear, right? The other thing I need, though, it's got to be hermeticity preserving. So what does that mean? It basically means that if it takes in a Hermitian operator, it outputs a Hermitian operator. Okay? Because otherwise this inequality won't make sense. So I have to make sure the output is Hermitian. Okay, so maps Hermitian operators, say on some input space x to Hermitian operators on some output space y. Okay? And so the last thing I want to mention now is I want to go back to this star, which I didn't define this Psi star. That's this adjoint of this map. So let me define that Psi star. So this is the adjoint map, by the way. Well, let's just write this down. Psi star, right? And this just goes in the opposite direction, right? So psi over here went from Hermitian x to Hermitian y, and this is just going to go in the opposite direction now. So it's going to take us from y to x. So Hermitian operators on y, whoops, to Hermitian operators on x, right? And what is the property of this map, right? is the unique linear map such that, and here it's very important here that I say for all linear operators A and B. Oh, well, okay, sorry, the spaces can be different, right? So this is a linear operator on Y, B is a linear operator on X. So given any pair of linear operators on the right spaces, basically, if I take the inner product of A, and not with B, but with psi of B, right? So this is my same psi as before. Remember, psi took me from X to Y, and that's why, this one, as you can see, lives in Y, and psi of B also lives in Y, right? So now the spaces match. The point is that the adjoint is the only linear map which satisfies, instead of doing it on the right-hand side of this inner product, I can do it on the left-hand side. So I can do psi star on the left on A. That's the property we're looking for. Okay? So that is kind of the full breakdown I want to do of STP. Sorry, let me just show you the STP again, just so, just to recap, right? So we had you want to maximize overall positive semidefinite X, basically, that satisfy this constraint, and you want to maximize this cost function. And the dual, once you have this, you can immediately write down the dual. Well, immediately in the sense that you kind of have to work out what psi star will be, and we'll do an example of that shortly. But then you just want to now it's a minimization. So you'll notice that the primal is maximizing, right, like this, and the dual is minimizing, right, and it's coming down. And we're going to say something about that shortly. That's important. Okay, that's the basic idea. Okay. And what do I want to do next? Good. We're going to do a Psi Star calculation, right? This adjoint map. Let's do this one together because it's kind of weird at first. Like, how in the world do you come up with the map that, for all operators A and B, this holds? Like, what? Like, how are you supposed to do that, right? And this is what I mean by you typically need a bit of creativity with this. It's usually not too difficult, but, it's not trivial, let's say, right? So let's do an example. Let's suppose that psi is going to be the trace function. Okay, so that's why you'll notice that it takes some n-dimensional vector or operator or whatever, right? And it maps us to a complex number. Okay. I mean, so technically speaking, if you like, you can think of this as just being, the n diagonal terms on an operator, if you like, right? So you can, of course, embed this into a matrix function, if you like. Okay. Or you can think of the whole matrix as having n entries across all the rows. Up to you how you want to define this. Okay. So what did we want? Right. What does this say? So I need this to hold, right? I want to ask, what is psi star? Right. That's the question. Okay. So what does this mean? This means that I need the following, right? I need that for all A. And what is A? Let's get the spaces, right? So this is just going to be a linear operator on C, on the output space, right? This is this, remember it's on Y, the output space, and here's your output space, right? So in other words, for any scalar, this is really what this is just a scalar, right? And for any linear operator on the input space, Cn, basically, right? Oh, you know what? This is a type. I probably wanted to just write this, to be honest. Okay, let me adjust this in the notes. Where are we? Okay. Okay. So what do we need? We need that if I take basically the trace of the operator B, right? Because that's a linear operator acting on the second space, right? And I have this inner product, right? And I take the inner product with A, right? This is supposed to equal, right? What is this? By the way, this is this left-hand side, right? Here it is. I just applied psi, the trace function on the right-hand side. Of course, this is now a scalar. I just took a trace. And by definition, A is also a scalar. I just wrote that over here, right? So this basically product of scalars, well, technically you're taking a star here, of course, because that's the way the Hilbert-Schmidt inner product is defined. What I want is that this is supposed to be whatever psi star is, I haven't defined that yet, of A times B. Okay, this is what needs to hold. Okay. So what in the world is this? Like, how in the world am I supposed to figure out psi star so this holds for all A and B, right? So let's just dig a bit deeper now, right? So let's take this one out and try to really understand what's happening here, right? I'm just going to write A as A, right? Because capital A is a scalar, and so I want to write it as a small letter just so it's really clear kind of when you just look at it that it's supposed to be a scalar, right? So therefore, this inner product of this thing, what is that? It's just going to be, well, I'll just write it this way. It's just A times the trace of B, right? That's all it is. Okay. So now what do I have? So that's that one, the top one. And now what happens if I do this one now, right? The second one. Well, I still don't know what psi star is. I'm trying to figure out what psi star is, right? But I need this thing to equal to this. Okay, that's what I'm aiming for. But I know the definition of the inner product, right? I can just write it down. It's the trace of psi star of A, right? And then technically I need a dagger on this full thing, right? And then times B. That was just the definition of this Hilbert-Schmidt inner product. Okay. Now, what did I want? Well, you have to be a little bit careful here now, right? First of all, again, the first thing you should always do with these expressions is understand the objects that are sitting in them. Okay, if you don't understand the objects, then there's no way you're going to understand what the expression is trying to say, right? So remember that capital A is really nothing other than a scalar. It's just this little a which I defined here, just for convenience. Okay, so, and it's Hermitian, so I can assume that that's a real number and not a complex number, so I'm not going to bother carrying around this dagger over here. I'm going to drop that. Okay, so this is technically what I need to be true, right? And then, well, now this is a scalar, right? Well, sorry, that's not true. I take that back. What is this? Whoops. By the signature of this thing, right? Let's go back. Let's just do a sanity check, right? Psi star was supposed to take me from my output space, in my case, the complex numbers. Where did I write that? This is the output space, the complex numbers, back to the input space, which is this n-dimensional space. Okay? So this thing here is a linear operator on Cn. Okay, so it takes a scalar and it blows it back up into a matrix, right? And now the question is, I get to define how that blow up happens, right? Because I haven't defined psi star. I'm trying to figure out what choice of psi star would work, right? And so how in the world do I make it so that these two guys are equal? That's my goal, right? I'm trying to make it so that whether I apply, remember this thing was nothing other than psi of b on the right, whether I apply psi of b on the right or psi star of a on the left, I should get the exact same thing out. And so if only I could make this thing kind of just equal to a and kind of disappear out of the picture, right? Out of this trace, then I would get exactly a times trace b. And so here's where the slight creativity comes in, which is that what happens if we define psi star of a as just the map which takes the scalar a and maps it to the operator a times identity. Okay, let me do this. Times b. Okay, so here all I'm saying is I'm saying define psi star of a to be equal to a times identity. Okay, for any a you give me, doesn't matter which one, of course, right? Then what is this? Well, this is easy now, right? This is literally just the a times the trace of b, because a is a scalar, right? That's it. And we know, I've already told you, right, that this map is unique, right? So, you know, here's one choice that works, and so one choice of psi star which works, right? And so that's it. There's no other choice, basically, right? So this is, you know, a cute little example that shows you how, you know, given the map psi, you can kind of use this constraint that these two should, well, not this one, but this constraint that needs to hold. You can use this to figure out, given psi, what should psi star look like as a linear map, okay? Okay, so that fully, let me just remind you, we're just doing that because the psi shows up in the primal, right? But in the dual, we get psi star. The other final thing I'll mention is that normally in this course, you know, we're thinking about, you know, have a vector like a quantum state, and I hit it with a matrix to take it to another vector, and those is what we were calling operators. Now this thing, I mean, you could always view these psi's over here You can view these as operators as well. Like if you take your matrix and stretch it out so it looks like a vector, you can also do the same thing. But technically speaking, when you're mapping matrices to matrices, these things take on a special name. At least in quantum information theory, we tend to call them superoperators. Okay, and I'm not entirely sure if that name extends beyond quantum information theory, but certainly this is a standard terminology for us. Okay, in this course, we will not study superoperators, like at least in a formal sense, let's say. But pick up any quantum information textbook. There are certainly a few by some very nice authors out there. I don't want to play the recommendation game for things you would, in principle, have to purchase, so let me not go there. But you can learn all about superoperators elsewhere, but unfortunately, we won't do it in this course. Okay. So that's the basic definition of a semi-definite program. And now I'm sure you're staring at this and saying, what in the world is this, right? What kind of weird cryptic mess have I gotten myself into, right? So let's just do some examples, right? And the best place to start always is to remind yourself that typically, no matter how nasty or complicated something looks, there's a very good chance you already know how to do it, meaning you're comfortable with a special case you've been doing for much longer than you think. So the simplest example of an STP, which I want to do now, is something that you've been doing since the start of this course, actually. We just didn't call it an STP because an STP is just one of the ways to compute this thing. That thing is the largest eigenvalue of a Hermitian matrix, let's say. Okay. So here's an example STP. Compute the largest eigenvalue of a Hermitian C in, okay. And so how do we do this? How do I write this as an STP, right? Well, I claim the following. So here's your primal. It's going to be the supermum over the trace of Cx. And remember, x is my variable, right? Maybe I'll just always write, maybe I'll just always write that in red. Okay. Subject to the constraints that the trace of x is at most 1. So now it's a scalar one because it's a trace. So I don't need the generalized inequality. X is positive semi-definite. Okay. So what's C? C is this one over here, right? So I claim that this thing computes the largest eigenvalue of C, right? And intuitively, why is this true? Well, the best you could do here is what? I mean, remember, if you take a spectral decomposition, the best you could ever hope to do is write x as lambda max, the projector onto that top eigenvector, right? And certainly that will be, this thing will have trace precisely 1. So it'll satisfy this constraint. And of course it's positive, it's just a projector. Okay? This also goes back to that, the name of that characterization, the min-max characterization of eigenvalues, which I always like to think about, but whose name I always forget, the Cauchy, apologies to the second author, equality, which we saw in an earlier lecture, this variational characterization of eigenvalues, right? Where you're kind of maximizing over one-dimensional spaces if you want, say, the top eigenvalue, and that's what this will do. Okay, so I'll let you think more about why that should give you the top eigenvalue if it's not clear to you. The dual is now the super simple, which is the infimum over all scalars. Now it's a scalar. Subject to the constraints that y times identity is at most C. Okay? Now, why in the world should this thing characterize largest eigenvalue, right? I mean, here's your C, and you're upper bounding C by something times identity, and you're scaling the identity, right? And remember, identity always diagonalizes in the same basis as C. So all we have to do is compare eigenvalues of y times identity to eigenvalues of C. And what we need is that all the eigenvalues of y times I should be at least as big as all the eigenvalues of C, on a per case basis, right? And so obviously, the smallest you could ever hope to set y is going to be the largest eigenvalue of C. Okay, otherwise you'll violate this. Okay, so that's a very nice, simple example of an STP where it's doing a computation which you've been thinking about already for quite a while. Okay, now, two comments I want to make. As I said before, you don't always have to put your STP into standard form. Sometimes it's easier not to. So, in this particular example, we're not necessarily in standard form because I don't have the, where's my mouse cursor? There it is. I don't have the y greater than or equal to 0 constraint built in here, okay? The other comment I want to make, which is a bit more important, you'll notice over here, I said let's use a supermem, which is kind of weird, right? I mean, you never use a sup if you can get away with a max, right? So why in the world are we using a supermem? Well, the reason is because it turns out that it's not true that in general, for STPs, the optimal value of that objective function will ever be attained, okay? Meaning that you might have a limit of, inputs x, so that, this supermem gets closer and closer and closer to some point, but never actually attains that point in the feasible region. That's why this super is necessary. And here's is necessary in general. And here's an example, a simple example that shows where, you don't attain the optimal value. So here we go. So take the infimum over all scalars x, subject to the constraint of x1, 1y, right? And I want this thing to be positive, and x and y are just real. Okay, this is an STP. Again, it's not in standard form. And this is going to be exercise 23, and maybe we'll do it together now because I think it's worth taking a moment to think about, right? So what are you trying to do? You're trying to make x as small as possible, right? So that this funny matrix, where you have x on the top left, y on the top bottom right, is non-negative. And x and y can be any real number, actually, okay? Now, without loss of generality, actually x has to be positive. So why is that true? Well, remember that if I have, this matrix A, B, C, D, whatever that is, right? If I want this thing to be positive, the very first requirement is that, well, it should certainly output something non-negative. This should be greater than or equal to 0, right? By definition, because if I sandwiched it with any vector, right, it should go to something non-negative if it's positive. So that's if this thing is positive, right? And so what is this thing? Well, that's just A, right? You can always rip out the terms on the diagonal one by one by just putting in, the corresponding standard basis states. So I know already that x has to be positive semi-definite. So here already you see that, even though we just said x is real, implicitly, this constraint already enforces x to be non-negative. Okay, so the obvious thing is that you want to get to x equals 0, right? But the problem is that if I put in a 0 there, then this thing can never be positive, right? No matter what y I plug in. And so how do you see that? Well, the easiest way to see that is exercise 23, right? So we use this thing called the determinant test, right? Which says that for a 2 by 2 matrix, okay, it's more complicated in higher dimensions, but for a 2 by 2 matrix, it's very simple. A is positive semi-definite, if and only if, first, both the diagonal entries are greater than or equal to 0, okay? That's what we just talked about x. So x and y both have to be non-negative. And the other condition we need, right, is that the determinant of A should be non-negative. Okay, that's the kind of the more non-trivial property. So what is the determinant? Remember, the determinant of this matrix over here, for example, is equal to A times D minus B times C, right? It's this diagonal minus anti-diagonal. Again, only for two-dimensional matrices. In higher dimensions, it's a bit more complicated. And so what is the determinant of this thing? Maybe I'll do it down here. So the determinant, no. What is this? This is going to be xy minus 1, right? So in order for this matrix to be positive, I need two things, right? First, I need the diagonal terms to be 0, and I need the determinant to be 0. So this has to be 0, and x has to be non-negative, and y has to be non-negative, right? These are the three conditions I need to hold true, okay? And now we have a problem, right? If x is 0, right, over here, there's no way I'm going to satisfy this inequality, right? If x is 0, then I'm just going to minus 1 is greater than or equal to 0. I've failed blatantly, right? So x equals 0 is not in my feasible region. But if x is anything non-negative, like strictly positive, then there's always a choice of y that will kind of bring me back down to earth, if you will, right? So if x is like really, really tiny, then I can make y kind of as big as I like, right, as a real number, so that x times y is at least 1 in magnitude. Okay? And so what we see here is that any x strictly larger than 0 is feasible, along with the right choice of y to go with it to make sure that xy is at least 1, right? But x equals 0 is not. Ha, okay? So what that means is that, over here in this optimization problem, we have a sequence of solutions, right? Feasible solutions x comma y that get closer and closer to 0, but they never actually hit that infimum, okay? And this is why we need the inf, right? Because otherwise, well, it's not well defined, right? What is the answer to this STP? Well, you need to take the limit, okay? But the limit is not feasible, right? So we need the inf. Good. That's exercise 23. Now, the last thing I want to mention, well, technically the last two things I want to mention are duality theory and runtime, and I think then we'll close today's lecture, because then we're certainly over 2 hours, probably slowly getting to 2.5 hours, and that's a good time to cut the lecture. And then next class we can talk about, now that we have STPs, how do we write a quantum interactive proof as an STP, and then solve it in polynomial space. Okay, so if you think of semi-definite or convex optimization most generally, but let's just say semi-definite programming for purposes as a banana split, let's say, right? The primal semi-definite program in some sense is kind of like, say, your ice cream. The banana is duality theory. It's the dual, right? It's what makes that banana split so awesome, right? And what makes it so useful in this particular case, okay? So why in the world have I been carrying around this dual the whole time? So let P be the optimal primal value, and D be the optimal dual value. Okay? Now, what do we know? Well, remember the primal was always trying to maximize, right? That's just the way we wrote it, right? And the dual was always trying to minimize, right? What's the best way to write this? Maybe I'll write it this way. The dual was always trying to minimize, right? And a priori, it's not clear whether there should be a relationship between this dual and the primal, the values you get out of both, right? But the amazing thing is that there is a relationship. It's actually not that difficult to show, but I won't do it here in the interest of time. This is called weak duality. Weak duality says that the primal value is always upper bounded by the dual value. And all that really says is that this picture I drew here is accurate. The value of the dual is always lower bounded by the primal. Okay, seems like a very basic thing to say, but it's incredibly powerful. So here's a perfect example, right? So a lot of times, you're using an STP, and you can encode some difficult problem into the STP, right? So maybe you're talking, say, about a cryptographic protocol, and you can embed its optimum cheating probability, let's say, in terms of an STP, and you want to kind of upper bound that value. You want to say that the cheating probability is at most something small. Okay, you want an upper bound. But maybe solving that primal problem is very complex. It's very nasty looking. A lot of times, by moving to the dual, first, it will guarantee that if I can guess a good solution to my dual, I'll get an upper bound on my primal, right, by weak duality. And a lot of times, the dual can be rather simple, right? So, the very naive thing to do is usually you just kind of put in some scaled version of the identity just as a guess for the dual as a feasible solution. It's typically not the optimal solution, but who cares, right? Because often, all you want is an upper bound. It doesn't have to be the absolute best upper bound. As long as it's good enough for whatever purpose you have in mind, you can try a silly solution like the identity in your dual, and it will give you some upper bound on your primal. And in theoretical analyses, like in this crypto analysis example I gave, that's often good enough. Okay, so you don't have to pull out your STP solver. You don't have to code anything up. You just do it all on paper, and you just get a rigorous upper bound by duality theory on your primal solution. Amazing. Okay, So this gets used all the time, more so, of course, in the theoretical analysis side than in practice, right? In practice, you would actually solve the SDP. Okay, and now you might be wondering, is this tight? Meaning, is it true that these guys always meet in the middle? Okay, does the optimal dual value equal to the optimal primal value? Would be a lovely world, wouldn't it, right? For linear programming LPs, yes. Okay, there we have that P equals to D, always. Okay, the optimal solution for the primal is equal to the optimal solution for the dual. Of course, if you choose non-optimal solutions, then you still get this weak duality still holds. But when you choose optimal ones, you get equality. For SDPs, no, unfortunately not. So we can have that the primal is strictly smaller than the dual in general. Okay. So the good news, however, is that often you do get equality. Okay. And not only that, but you can usually check. There are kind of constraints, qualification conditions you can check to make sure that whether or not this equality will hold or not. So first, let me be clear that we say that if P equals to D, right? And I think you might need the primal dual solutions to actually be attained, not be suprema, but let me kind of ignore that point for now. We say that strong duality holds. Okay, so not weak duality, but strong duality. And in general, this doesn't hold, but there is a condition you can check that's usually quite easy to check, which is called Slater's constraint qualification. And what does this say? This just says, it's just a condition on which, condition you can check to see if strong duality holds for your primal dual pair, right? And so what does this mean? This is just, there exists a strictly feasible X. Okay, what do I mean by that? I mean that phi of X is strictly smaller than D, and X at the same time is PSD, strictly bigger than 0, so it's positive definite. So remember that the primal was trace of CD. We want to maximize this. Sorry. I apologize. Superman, right? Trace of CD, CX, right? Subject to the constraints that phi of X was less than or equal to D, and X is positive semidefinite, right? So strictly feasible just means that, of course, we don't have equality here, right? All your eigenvalues of X, for example, are strictly positive, for example. Okay. So if such a solution holds, this solution, this strictly feasible X, could be a terrible solution. It could be nowhere near optimal. Who cares? It's sufficient to have such a solution to argue that, okay, yes, indeed, strong duality does hold. So if I were to find the best primal and dual solutions, indeed, their values will match. Magic. Okay. And so I'm going to give you an exercise. Maybe we won't do it here. Exercise 25. And basically it looks like this. Infimum of X, subject to the constraints that 0x, x, y, 0, 0, 0, 0, x plus 1 is positive semidefinite. X and y are just reals. And the claim is that this thing fails strong duality. Okay. Now, intuitively, the reason why it should fail strong duality, right? What does it mean? Well, okay, this is not enough to conclude it, right? But what you might try and do is you might try and check if Slater's constraint qualification holds, right? Which means that there's some setting to x and y, these are my variables, which is strictly positive, and so that this inequality holds with strict positivity. okay? But the problem is that, if you just look at this kind of first block, right? In this block, because I have 0x, x, y, right? If x is strictly positive, right? Then in general, this thing is not going to be PSC, this block, right? I mean, you've got zeros here, right? So this 2 by 2 block, by the previous exercise, remember, this thing is positive if and only if the determinant is positive, along with the non-negative values, right? Diagonal values, right? So, 0 minus x squared, right? So as long as x isn't positive, right, as would be required by strict feasibility, by this condition here, right, this thing here would be not positive, right? And so you would fail this condition. Okay, so already you see that you cannot apply Slater's constraint qualification. Now that alone is not enough to guarantee that this does not satisfy strong duality. This is not an if and only if condition. Let me really stress this, right? Slater's constraint qualification is a sufficient condition to say that there is strong duality. If Slater's constraint qualification does not hold, we can't necessarily say anything about strong duality. Maybe it holds, maybe it doesn't. Okay, so here, Slater's condition fails, but it's still possible that strong duality could hold. So I'll let you kind of finish the analysis of this, but at least right now you immediately see that x has to be 0, otherwise there's no way you're satisfying this thing. Okay, and I'll let you, so you must set x to 0 in the feasible region. Okay, and I'll let you kind of go forth and conquer from there, let's say, right? Good. The last thing I want to mention in today's lecture is runtime. Okay, obviously we're not going to cover algorithms for solving STPs in this course. Well, that's a blatant lie. We are going to cover an algorithm. We're going to cover the matrix multiplicative weights method, which will give you an approximate solution. It won't do it exactly, right? And the advantage is that we're going to be able to kind of parallelize and put in p-space. But of course, in practice, you typically won't use this, right? In practice, you're going to use more advanced methods. So let me just tell you a bit about those, but I won't show you anything else. Okay. So in general, a lot of times when you look up STPs, particularly in the CS literature, like CS theory literature, let's say on algorithms, they'll just like wave their hands and be like, yes, STPs can be solved in polynomial time. Rubbish, right? The truth of that, like the underlying intuition behind that statement is true. In practice, most STPs can be solved efficiently, but it's not true that all of them can be solved efficiently. There are some kind of very mild preconditions that are necessary for like algorithms like the ellipsoid method to actually run in polynomial time. And I just want to make you aware of these. Okay. So to solve an STP in poly time, so what we do is we need two parameters, right? So let me say, so we need, number one, the feasible region is contained in a ball of radius r, capital R. Okay, so I mean, let's just imagine that we had some feasible. Oh, by the way, this is absolutely terrible because that's not a convex region. Okay, so there's my feasible region. Let's just think of this as all the assignments X which satisfy all the constraints we need to. So this has to be contained in some ball, right? R. I'm terrible at drawing balls, and ball depends, I suppose, on your choice of norm and things like this. But you're contained in some big sphere, let's say, of dimension R, whatever sphere should mean in your setting. Okay, and you also contain a full dimensional ball. You must contains a ball of a dimension, of radius little r. Okay, and when I say ball, I really mean a full dimensional space. So if you're working in, say, Rn, your feasible, in our case, our feasible solutions were operators acting on Rn. That means that there's a ball, a hypersphere of dimension n, okay, that's sitting in your space. So in other words, your feasible region has to be full dimensional. It's not some lower dimensional kind of flat subspace, okay? Good. Then, the runtime, and usually when you're talking about theory, we take the most kind of well-known algorithm, let's say, which was developed, I think, in the late 70s by Hachian. And that's the ellipsoid method. Right? And the runtime is going to be polynomial in what? In what? Well, the input, right? And so by that I mean kind of like the encodings of, everything like your constraint matrix, your Hermeticity Preserving constraint map, and so forth, all the operators that went into it, right? And typically we assume that these operators are, to specify them, you're using at least a dimension space, right, to write the full thing down, and you're not using any funny weird succinct encoding. This is true for the ellipsoid method. Of course, when we get to STPs for interactive proofs, we're going to break that convention, right? Because like the operators we come up with will have to do with quantum circuits, which we cannot, of course, explicitly write out the full matrix for, right? That's kind of the challenge. Okay. So in that, it will run in time polynomial in log of the radius r. Sorry, that's this radius, right? And I totally forgot to draw my little baby ball. Here it is. And this thing has radius little r, right? That's my inscribed ball, right? And this is the circumscribed ball, the big one. Okay, so it runs in time log of the big circumscribed ball, and then the log of 1 over little r for the small baby ball contained inside. Okay, and finally, the last thing you're probably wondering is there's no way we can solve these things perfectly, especially if we're not even guaranteed that the superminimum is always attained. So there's going to be some precision, right, error. And that's exactly what epsilon is. This is going to be your additive error for the solution. So if you want to, say, solve your STP to within plus or minus epsilon, then the cost you pay for that is log 1 over epsilon. Okay, that is really, really good, right? Because that says that you can get inverse exponential precision, basically, in polynomial time. Okay, assuming, of course, that these things are nice too, right? I mean, so as long as r is not, say, big R is not doubly exponential, right? You're good. It'll run in polynomial time. Good. And the last thing I want to mention is that I've mentioned ellipsoid method here. Nobody in their right minds uses the ellipsoid method in practice, right? It's incredibly, well, to put it nicely, nasty, right? It's very, it's not, what's the word? It's not stable at all. It's very unstable numerically speaking, right? That's a whole other topic in of itself. Like many of the operations we take for granted, like matrix inversion, we've talked about this condition number, right? And the ellipsoid method is another example of an algorithm which can be numerically unstable, right? In practice, you would use much more modern methods like interior point methods, okay, to solve STPs. Again, we're not going to use these in this course, so I'm not going to say anything more. Again, I refer you to this really nice textbook of Boyd and Vandenberg, which is probably a good 10 to 20 years old now, but it's wonderful. It's very well written mathematically. I love that book. Okay, I'm going to stop there for today. The next section would have been, and as in we're going to continue next time, quantum interactive proofs as STPs. Okay, so that's going to be basically bottom of page 7 of the notes. So we're essentially right in the middle of the notes, which is perfect. We'll cut here. So this week, let's just recall what we did, right? We defined the multiplicative weights method on real numbers, basically. Then we defined quantum interactive proofs in the class QIP. And then we defined semidefinite programs. Okay, and next class, what we're going to do is we're going to show first how to write a quantum interactive proof as a semidefinite program. This is going to be section 2.3. And then we're going to take that semidefinite program and combine it with multiplicative weights to solve it. Matrix multiplicative weights, a matrix version. We're going to solve it in polynomial space. And that should be in section 3, generally speaking. Okay? And that should eat up the next lecture. And that will be a wonderful holiday present for you to take home during your break. Okay, so that's all I have to say for this week. As always, stay healthy. If you have any questions, let us know. And we'll see you in 1 week. All right?